Hello everyone, my name is Komasinyolo. Welcome to another video by Attention Matrix, where we try to make learning fun and easy. Please comment, like, and subscribe if you would like us to continue making this content and you enjoy it or find it helpful. Now on to the next video. Let's get right into it. Okay, hello, welcome to my video lessons. In this video, we will be focusing on vertical projectile motion, and we will be looking specifically at a problem, an example from a past exam paper. That is what I will be solving in this problem. I introduced the concept of vertical projectile motion in my first video, and here I'm just demonstrating the principles that I explained in the first video. So to demonstrate these principles, I will be looking at a specific example problem, which is question 3 from a past exam paper. Okay, so this is the question that you see here on the screen. So the question is as follows. It says an object is projected vertically upwards at 8 meters per second. Okay, so this is how we know that we are dealing with vertical projectile motion, because we are told that it is projected, it is thrown vertically, right? It is projected vertically. So this is vertical projectile motion. So an object is projected vertically upwards at 8 meters per second. Now, what is that 8 meters per second? That 8 meters per second is a velocity. Okay, I've covered the parameters for the equations of motion or for vertical projectile motion in my first video, and I highly recommend that you watch that first video if you have not, before continuing with this video. Okay, so I'm just gonna keep repeating myself to hammer these points home. An object is projected vertically upwards at 8 meters per second from the roof of a building which is 60 meters high. Okay, so the roof of the building is 60 meters high. That's the roof of that building there. It's shown there, and then the object is thrown from that position there on top of the roof. So there's a person standing there, and then they throw the object upwards, and then the object travels all the way as shown there on the screen. Okay, or on the question. So an object is projected vertically upwards at 8 meters per second from the roof of a building which is 60 meters high. It strikes the balcony below after 4 seconds. Okay, so once this object has been thrown, it goes up, changes direction, goes down, and then it strikes the balcony. And by the time it strikes the balcony down there, 4 seconds have gone past. Okay, so from the moment that the object was thrown from the roof to the instant that it struck the balcony further down, 4 seconds went by. Okay, the object then bounces off the balcony. It bounces off the balcony and strikes the ground as illustrated below. So after striking the balcony there, it bounces off and then goes and falls on the ground like that, as shown on the diagram in the picture. Okay, so on the diagram in the question. So then they ask us the following. They say, okay, for 3.1, let me just try to exit this thing. Revert to original, discard. Okay, so this is the question, right? For 3.1, it says, is the object's acceleration at its maximum height upward, downward, or 0? Is the object's acceleration at its maximum height upward, downward, or 0? This is 3.1. Now, what are they asking us in this question? So this is what they are asking us. Okay, so they want to know if, so you've got a building, right? You've got a building there, and then you've got somebody on the building with an object. Somebody on the building with an object. There's a balcony further down there. Okay, and then the height of this, the overall height of this building is 60 meters. Okay, so the overall height is 60 meters. So the object gets thrown, it goes up, it strikes the balcony, and then it goes up again, and then it hits the ground. It lands on the ground, okay, which is 60 meters below from the point at which it was thrown. So now for 3.1, for question 3.1, what they are asking us is about the acceleration, the sign of the acceleration, right? They want to find out about the sign of the acceleration. So what they're saying is the object's acceleration at its maximum height upwards, downwards, or 0? So when the object is at its maximum height, where is the object's maximum height? The object's maximum height is there. Okay, that's the, let me change colors to represent the object. So the object's maximum height is there. It gets thrown from here, goes up, and then it reaches its maximum height. All right? That's where its maximum height is. And they're asking us at its maximum height. So when it goes up and then reaches its maximum height, what is the sign of the object's acceleration? Is it positive, negative, or zero? That's what they mean. Okay, so when they're saying for 3.1 there, if you look on the screen, is the object's acceleration at its maximum height upward? Upward means positive, right? Upward means positive. So if I come back here, this upward here, upward simply means positive, right? Downward means negative. Zero means zero. Okay, zero doesn't have a sign, it's just zero, it's itself. So that's what they're basically asking you there. Is the object's acceleration when the object is at its maximum height, is its acceleration positive, negative, or zero? That's if your sign convention, if we take up as positive and we take down as negative, right? You could have the opposite sign convention, but I'm not going to cover this here, just as to avoid confusion. Okay, so upwards is positive, downwards is negative. Okay, so when they say upwards, they want to know, is it upwards, downwards, or zero? Right? Is the acceleration positive, negative, or zero? Now, from my very first video, what do we know about acceleration? Well, we know that for vertical projectile motion, the projectile that is in motion is under the influence of gravity, right? In other words, it is accelerating at an acceleration that is equal to the gravitational acceleration. And what is the gravitational acceleration? Remember, I called in the first video, the gravitational acceleration is g, and the gravitational acceleration is minus 9,8, right? Minus 9,8 meters per second squared. That is the gravitational acceleration. That is the acceleration that is being applied on every object on planet Earth by the Earth, right? Every object on Earth is being pulled towards the center of the Earth at an acceleration. So every object on Earth is made to accelerate at an acceleration that is equal to the gravitational acceleration, which is 9,8 meters per second squared. So this object, regardless of where it is, whether it's here, whether it's there, whether it's there, whether it's there, whether it's there, or whether it's there, or whether it's there, you will remember from my first video, the object's acceleration is always towards the Earth. If you throw it up, it wants to move towards the Earth. It will fall. And by definition, to fall is to move towards the Earth's surface, towards the ground, right? So it is being pulled towards the Earth's surface at an acceleration that is equal to the gravitational acceleration, which is minus 9,8 meters per second squared. This value does not change. It does not change ever. As long as you are on planet Earth, this value does not change. It only changes if you are outside of planet Earth. But for all our problems, we will be looking at objects that are on planet Earth, or that are on planet Earth, right? So the acceleration of this object, regardless of what it is, whether it's a pen, whether it's a ball, whether it's a pencil, whether it's a TV, whether it's a plate, whether it's anything, right? It is experiencing an acceleration of minus 9,8 meters per second squared. So what is our answer? Well, our answer is downward, because it's minus, right? It's things that are on planet Earth are always being pulled down back to planet Earth. So the answer is minus. It's always minus. It doesn't matter if it's currently moving out. See, they mentioned the maximum height just to confuse you. They're asking you about when the object is at its maximum height, just to confuse you, right? When it's at its maximum height, the acceleration is negative. It's still negative, whether it's at its maximum height, whether it's in the person's hand, whether it's there, whether it's there, whether it's there, whether it's there. It doesn't matter where the object is. Its acceleration is always towards the Earth. Its acceleration is always negative. Okay, so that is question 3.1. Let's write that down a bit more neatly. So the acceleration of the object at its maximum height is equal to the gravitational acceleration, which is equal to minus 9,8 meters per second squared. Okay, meaning that for 3.1, the answer is downward. right? The answer is downward. And this is if your sign convention is downwards is negative and upwards is positive. Okay, so before solving any of these physics problems or these physics questions, right, it's very important to establish what your sign convention is. Now, your sign convention is basically you associating a sign, by sign I mean negative or positive, with a direction. So this is what I want you to do for every question that you start solving for these types of problems, especially in this chapter or in this section. You draw this little thing here, this little graph there, and then you say this one is pointing towards the right, right? So you make it positive. This one is pointing upwards, so it's positive. So this simply means that upwards is positive and that to the right is positive. You put this in, right? This is if you want to consider your upwards direction as positive, which is what I recommend, and if you want the right to be positive, which is what I recommend. Now, you could choose the upwards direction to be negative and you could choose the right to be negative. There's nothing wrong with that. You just have to be consistent when you're solving your problems. But I suggest that you always choose your upwards direction as positive and your direction to the right as positive as well. Okay, so this is the answer to question 3.1 based on the sign convention that I chose. Okay, so I hope this makes sense. If this doesn't make sense, please, I beg of you, revisit my introductory video on vertical projectile motion. In the video that I used to introduce this topic, I don't do any calculations. I just simply describe the topic. I explain the topic, I explain the concepts, I explain why things are the way that they are for this concept. I don't do any calculations, so please have a look at that video, the first video in this section. Okay, so now let's move on to question number 3.2. Okay, so question number 3.2 says calculate, so 3.2.1 says calculate the magnitude of the velocity at which the object strikes the balcony. Okay, so first let's gather our information, right? Let's go back to my video. This I'm gonna leave here and then I'm gonna move on to the next page. Move on to the next page. This icon is quite big. I don't know how to make it smaller. Anyways, just gonna do that. Okay, so for question 3.2.1, 3.2.1. So question 3.2.1, let's go back to the question. It says, calculate the magnitude of the velocity at which the object strikes the balcony. Okay, so let's redraw the scenario again. Okay, so let's redraw it again. So we've got a building. We know that the building is 60 meters high. 60 meters high from the ground. We've got a balcony here. We've got an object that has been thrown. Draw it in a different color. Object has been thrown from here, it moves there, lands on a balcony or bounces off a balcony and then to the ground. Okay, and we know, let's go back to the question. So if you look at the question again, it says an object is projected vertically upwards. Let me just mark things out as I talk. Right, an object is projected vertically upwards at that velocity, 8 meters per second, right? 8 meters per second. What is meters per second? Meters per second is a velocity. So when it's right there at the very beginning, the velocity is thrown up at a velocity of 8 meters per second. Right? That's the velocity at which the object has been thrown up. It leaves the hands, or it leaves whatever it's been thrown up from, at a velocity of 8 meters per second. So that's the starting velocity. That's the initial velocity. That's the velocity at the beginning, right? So we call that VI. So VI, or the initial velocity, is 8 meters per second. Why VI? Because it's the velocity that the object started off with, right? Once it has been thrown, it goes up and then reaches its maximum height. You'll remember from my first video that the object will go up and reach its maximum height, and then it'll go back down and it'll bounce off the balcony there. Then it goes up again. It goes up again, and then it goes or falls all the way to the ground. Okay, so that's what happens. Now, we've got 8 meters per second as the initial velocity from the roof of the building. Okay, so an object is thrown vertically, projected vertically upwards at 8 meters per second from the roof of a building, which is 60 meters high. I've already written that down. It strikes the balcony below after 4 seconds. Okay, so after 4 seconds, it strikes the balcony. So from the moment that it leaves this point to the moment that it strikes that balcony, it took the ball 4 seconds, right? So it moved from there, went all the way there, and the trajectory of the object, or the travel path of the object, took 4 seconds from the point that it was thrown from to the point that it strikes the balcony. That's what we know. Okay, so that's what they're basically saying to us. So now the object then bounces off the balcony, and then strikes the ground as illustrated below. Okay, fine. Now that we've gathered all of our information, we've taken our initial velocity, our time, and we've taken that there. So we've recorded all of that. It's very important to record the information that you have before you start solving the problem, so that you can easily access it. Okay, now let's go back to 3.2. Okay, so for 3.2, calculate the magnitude of the velocity at which the object strikes the balcony. Okay, so now we are asked to calculate the magnitude or the size of the velocity at that point. Right? They're saying at the point where the object strikes the balcony. Where it strikes the balcony, it has that velocity. So that's what we are required to calculate, the final velocity. Now, why am I calling this the final velocity? Because that is, you are looking at the object from the moment that it starts moving from there to the moment that it strikes the balcony. Now, the question will dictate what the final velocity is, right? If they had asked us for the velocity at a different point, the velocity at that point would be the final velocity. So for instance, if they had asked us for the velocity of the object at that point, then that would be the final velocity that we are looking for. If they'd asked us for a final velocity at that point, that would be the velocity that we're looking for. But in this instance, in this question, they asked us for the final velocity at the point where the ball bounces off the balcony, which is there. And so this is why that is my final velocity. Okay, so over the period of time that you are looking at the object, the last velocity over that period of time is the final velocity. Okay, so here you've got a time of 4 seconds. After 4 seconds, the ball is at that point, or the object is at that point, and it started off at that point. Now, this is all the information that we have, right? This is all the information that we have. We've got an initial velocity, we've got a time, and we are looking for a final velocity. This is basically what we have. And then we've got this 60 meters here. And then so let's see what information we can use, what information we can use to get an answer, right? So we go to our equations of motion. Now, this is in your formula sheet. I've got the formula sheet here. Okay, so here the first table here, the table at the very top is your equations of motions, right? It has the equations of motion. So this table here. So how you use this table is, firstly, you look at the information that you've been given, right? You look at the information that you've been given, and once you have all the information that you've been given, once you've established what information you've been given, then you can choose the relevant equation of motion to use to solve the problem, right? So now if I go back to the screen, what I have here is I've got an initial velocity. Okay, cool. I've got a time, and I'm looking for a final velocity. And this really won't help me much. This won't help me much because it's just the height of the building, right? It has nothing to do with the ball. Or the object. It's just the height of the building. So the information that is related to the ball is the initial velocity and the time, right? That's what I've been given. So let me just remove this stuff. Okay, so now I go back to my equations of motion. If I look at my equations of motion, okay, so let's start off with the first one. Let's start off with this one. Okay, so does it have the information that I've been given in order to enable me to be able to solve for what I'm looking for? Okay, what do I have? In my first equation, I have delta t. Do I have delta t? Yes, what is delta t? Delta t is time, right? My delta t is my time. So the time that I've been given in the question, if you remember, is 4 seconds. So I have my delta t. Okay, cool. Now, do I have a? What is a? A is acceleration. Do I have acceleration? Well, we know that an object, any object that is on planet Earth, is accelerating towards planet Earth at an acceleration of minus 9.81 meters per second squared, right? Minus 9.81 meters per second squared. So yes, I do have A, right? I have A. And then do I have I? Do I have I? Yes, I've got I. From the question, you'll remember that I was 8 meters per second. And I have been asked to solve for VF. Sorry, VI. I think I called this I. This is VI, right? VI. I have VI. VI is 8 meters per second. Now, VF is what I've been asked to solve for. So it seems like in this question, we're actually very lucky because the very first equation of motion that we looked at, we can use that equation of motion to solve our problem, right? We are asked to solve for VF and we've got everything else. So let's go ahead and solve. So it looks like this is the right equation to use. Just to hammer this point home, for instance, I could not use this equation. I could not use any of these two equations because I don't have this delta y or this delta x. I don't have them, so I could not use this equation, right? The same applies for this equation, these equations there. I don't have, what is this? I don't have delta x, so I can't use that equation. But in this case, I've got delta t, I've got a, I've got vi, and I need to solve for vf, and that is why I can use this equation. I hope that makes sense. Okay, so let us go on and solve. So what is our equation? Well, our equation is, use black, our equation is VF, you don't have to memorize this equation, right? You can get it from your book, like I said, from your formula sheet. Okay, plus delta t, I think I'm making a mistake, A times delta t, A times delta t. Okay, cool. So this is the equation that you can use. You've got all of this information. So all you do now is plug it in. Right, so what is VF? That is what we've been asked to calculate. Our final velocity at the point where the object bounces off the balcony is equal to the initial velocity VI. What is our VI? VI is 8 meters per second. So this is 8 in the upwards direction, right? It has been thrown up, so it's 8. It's plus 8. Remember, sign convention is very important, especially for your vectors, right? If you're dealing with a vector, always include the sign. Please, always include the sign if you're dealing with a vector. From the first video, remember what your vectors are. Your velocity is your vector, your displacement is your vector, your acceleration is your vector. Always put your sign in for your vector, okay? Downwards is negative, upwards is positive. Remember that, do not forget that. Okay, so you've got plus 8, you've got 8 in the upwards direction, that's why I put the plus sign there, plus, now you've got your acceleration. From question 3.1, what is your acceleration? And from the first video as well that where I explained this concept, what is A? A is minus 9,8, right? Minus 9,8. Remember, the sign is very important. Your acceleration is always negative. For the sign convention, always negative. Please do not forget that wherever you see your acceleration for this sign convention, use a negative sign. Please use a negative sign. It's a vector. Use it. Do not forget it. Okay, otherwise your answer is going to be wrong. Okay, so now we've got our A, we've got our VI. Now we need our delta t. What is our delta t? From the question, our delta t is, where's our delta t? Our delta t is the time at which the object moved from that point to the balcony. That time is 4 seconds. So then that's going to be 4 seconds here. It's going to be 4. Right. And then now you can solve for your VF. So if you solve for your VF, this is 8 plus minus 9,8 times 4, right? Let's go to my calculator. So you've got 8 plus open open bracket, minus 9,8 times 4 seconds. Your answer is minus 31,2. Sorry, I think I made a mistake there. What is it? I didn't make a mistake. I punched in something extra. So you've got your VI. Your VI is 8 plus your acceleration is minus 9,8 times 4 seconds. Okay, so that's the answer. 31,2 minus 31,2. What does the minus indicate? Okay, let's go back to our screen there. So your answer is minus 31,2 meters per second. This is your final velocity just before the object bounces off the balcony. Now, what does that minus mean there? What does that minus mean? That minus means that your ball is traveling downwards just before it, or I keep saying ball, your object is traveling downwards, right? Your object is traveling downwards. So what does that mean? It means that just before your object strikes the balcony, just before this object strikes the balcony at that point there, it's moving downwards. And that makes sense, right? If you're looking at the way this thing is moving, I'm going to redraw it down here. If you look at the way it's moving, right, you've got a building, the thing gets, okay, you've got a balcony there, and then the thing gets thrown from the top. It gets thrown from the top there, and it goes up, reaches its maximum height, and then it goes down. It changes direction and goes down, it goes down, and then it strikes the balcony, then it goes up again, and it goes down to the ground. Now, you can see that it's clearly moving downwards. It's clearly moving downwards before it strikes the balcony there. It's clearly moving downwards. And this is why your answer here is negative. This is why you've got that negative there. It's just to tell you that your object is moving downwards before it strikes the balcony. And so your calculations match up with reality. They make sense. They are practical. They are realistic, right? So it's very important that you check yourself in this regard. So if you got a positive number, you would be able to tell that no, something is wrong here, because this thing is moving downwards before it strikes the balcony. So I can't be getting a positive answer. It has to be a negative answer. So that's how you check yourself. Just make sure that these things make sense. Relate them to real life, right? It's not just theory that we're not just writing down numbers and trying to come up with a number. You just make sure that the thing that you write down, the answers that you get, make sense, and think about practical things in real life. If you throw a ball upwards and it comes back down and it bounces, before it bounces off a surface, it's moving downwards. Then after it bounces, then it goes up, right? So yeah, so that is the answer to 3.1.2. Okay, so another way you can express this answer, if you don't want to include signs, you could say your final velocity is equal to 31,2 meters per second downwards, right? Show the arrow. So if you don't use the sign, then you can use the arrow, but never use the sign and the arrow at the same time. So this is wrong. This minus 31,2 meters per second down, this is wrong, right? This is wrong. You either use the sign on its own or you use the arrow on its own, but never use both at the same time. Okay, this is just convention, and this is how we do things. Okay, so that was 3.2.1. Now let's go to 3.1.2. Okay, so 3.2.1. 3.2.1, these adds. Okay, so 3.2.1, go back to the question there, discard. Okay, so 3.2.1, or 3.2.2 rather. 3.2.2 says, let's come here. It says, calculate the height, right? Calculate the height calculate the height h of the balcony above the ground. Calculate the height h of the balcony above the ground. Okay, so let's go back to our thing there. This is actually 3.2.2. 3.2.2. So I'm going to redraw the building. You've got the building there. You've got the balcony. You've got the height of the building. That's 60 meters. Now they want you to calculate the height h of the balcony. So there's the balcony there, right? There's the balcony. I'm not going to write down the full word, but there's the balcony there. Okay, so they want you to calculate the height, h, of the balcony above the ground. So that is what we are going to do. So now, if I go to the next page, I'm going to keep redrawing this thing. Remember how your thing travels. Your thing, there's your balcony there, there's your 60 meters there. There's your 60 meters there. Remember how your object travels, right? So your object moves from the top there, it goes down, it bounces off here, then it goes down to the ground. Okay, so now they're asking you to calculate the height of the balcony above the ground. How do you do that? Okay, so how do you do that? Well, firstly, here's what I know. I know that the height of the balcony above the ground, the height, this height, let me try to scroll up. This height is equal to this height of the building minus whatever the height is there, right? Let me explain this. So there's the height of the building. The height of the building is 60 meters, right? The height of the building is 60 meters. Now I've got h, which is the height of the balcony above the ground, which is what we're looking for. So the height that we don't know is that portion there. We don't know what that height is. So I'm going to call this y. I'm just going to call it y, right? We know that, okay, so let's say we know that 60 meters is equal to, it's that 60 meters there, right? You can clearly see from the picture that 60 meters is equal to y plus h. Okay, when you take y and h and you add them together, you can see that this is equal to that, right? So when you take the two and you add them together, they will give you 60 meters. So that's going to be y plus h. Okay, we are looking for h. We do not have h. H is the height of the balcony above the ground, and that is what we're looking for. We do not have y, right? But how do we find y? Well, how do we find y? You will notice, and if you remember, if you had a look at my first video where I introduced this concept, y simply is the position of the object from the point at which it was thrown. So it was thrown from there, right? The object was thrown from there, and then when it bounces, right before it bounces, it's there, right? So that there is the displacement of the object from the moment that it was thrown to the moment just before it bounces, right? So that is what y is. So now this y, you can call it delta y. You can call it delta y. I'm actually going to call it delta y. It's fine even if you call it y. I'm just calling it delta y for the sake of the equations of motion. They call it delta y, right? So you can, there's nothing wrong if you call it y. You can even call it your name if you want. There's nothing wrong with that, right? So now how do we find this y? Because why do I need to find this y? Why? If I find this y, you will agree with me that I will be able to find this h, which is what we're being asked to calculate, right? So if I find the y, so let me rewrite it down here. So I've got 60 meters is equal to delta y plus h. Now I want to find this y in order to be able to find this h, because if I can find this delta y, then I know that h is equal to, this y will go to the other side and change its sign, right? So this will be equal to 60 meters, it's that 60 meters there, minus delta y. Now if I can find delta y, then I will be able to find h. Okay, so now let's go back to our equations of motion. If I go back to my equations of motion, here are my equations of motion again. You will remember this, we just spoke about it. There's your table. Okay, so there's your table, your equations of motion, your table there. Now, which equation can we use here to find delta y? Well, it's definitely not that, because there's no delta y there. It might be this one, right? It might be this one, and it might be this one. Okay, so I'm going to start from left going to right as usual. That's how I look at this. Okay, so now can I use this equation? And remember, I want you to notice something here. There's this part of the equation and there's that part of the equation. In this case, we are dealing with vertical projectile motion. Remember in the first video I said vertical projectile motion only focuses on the vertical direction. So these two equations represent the horizontal and the vertical direction, but you should only be focusing on the right where we have y, not x. X represents horizontal, y represents vertical. So you should only be focusing on the part where we have delta y. Right, so delta y is that equation there. These two equations are exactly the same things, just that one focuses on the horizontal, the other focuses on the vertical. So you just focus on the vertical because this concept, this topic, this section is vertical projectile motion. Okay, so now do we have Vf squared here? Do we have Vf squared in our problem? Okay, do we have Vi? Do we have 2a, and do we have delta y? Seems like we've got all of that information, right? We've got Vf squared, we've got Vi, we've got the acceleration, and we've got delta y. Now, it looks like we will be able to use this equation because we just calculated Vf squared, right? We literally just calculated Vf squared from our previous problem, and we have Vi, that's the acceleration, that's the velocity that was given to us initially, and then we've got our a, which is always minus 9,1 meters per second squared, and then we are looking for delta y. Okay, so we can use this equation, but out of curiosity, let's see if we can use the second equation as well. Can we use this equation? Can we use this equation? Let's see what we have. We are looking for delta y, right? Do we have Vi? Yes, we do have Vi. It's been given to us in the question. Remember, it's the 8 meters per second. Do we have delta t? Yes, delta t is 4 seconds, been given to us. Do we have a? Yes, we've got a. A is minus 9,81 meters per second squared. Do we have delta t squared? Yes, delta t squared is time, which is 4 seconds squared. Right. Okay, so it seems like, yes, we can use this equation as well. All right, so we can use this equation. Now let's look at the third equation, this equation here, right? The third equation. Okay, so do we have Vi? Yes, we've got Vi. It's been given to us as 8 meters per second. Do we have Vf? Yes, we just calculated Vf from our question that preceded this one, so the previous question. So we've got Vf. Do we have delta t? Yes, we've got delta t, that's 4 seconds. So it seems that we can use this equation, we can use this equation, and we can use this equation. What do you know, right? So we can use any of these three equations, and the answers that we're going to get is exactly the same. We can use any of these three equations and we'll get the same answer. We're looking for delta y. We can find delta y from any of these three equations. Now, I'm going to choose the simplest equation because I like keeping things simple, right? I'm going to choose the simplest equation, but trust me, you can use any of these three equations. I'm going to choose the simplest one, which is the last one, which is this one, because there aren't any terms that are being squared. So I'm going to use the last equation here. Okay, but you can use this equation. You'll get the answer that I'm going to get. You can use this equation. You'll get the same answer that I'm going to get. So you can test. Actually, this is an interesting exercise. Try it out on your own. Use all these equations as practice and learn how to use them. Use all of these equations for this question and see what answers you get. Okay, this is an interesting exercise. So I'm going to use this equation. So delta y, that equation, okay, to find delta y. So simply because it's the simplest equation to use, I like keeping things simple. I suggest that you keep things as simple as you possibly can whenever you can, right? So delta y in this case is equal to, so that equation says it's Vi plus Vf divided by 2 times delta t. Right, Vi plus Vf divided by 2 times delta t. Okay, so this is what I'm going to use. So I'm simply going to substitute here now. Okay, so what is my delta y? Delta y is what I am looking for. I don't have it. Okay, what is my Vi? My Vi is 8 meters per second. It's been given to me in the question, right? 8 meters per second. 8 meters per second. In the original question, that is the initial velocity that was given to me. So I am going to say 8 meters per second, right? Plus, because there's a plus there, Now, what is my final velocity? My final velocity just before the ball bounces off the balcony is, where did we calculate it? Is that, right? 31.2 meters per second downwards. Now, what must I do? Because now it's in the downwards direction. This velocity is in the downwards direction. How must I write it in my equation? As a negative, right? Please do not forget that. That's very important. As a negative. So it's minus 31,2. Minus 31,2. Put it in brackets and then divided by 2. All of that times 4. Okay, times 4. Right, that is your equation. And now you can solve this equation, solve for delta y. Please do not forget to write down the signs. The sign is very important for your velocity. It's downwards, so it's got to be negative. Right, so now let's come back here. In fact, I still have it there, minus 31,2. So now let's substitute things in here and see what we get. So we've got 8 plus, open bracket, minus 31,2. And then you come down here, you put in the 2, come to the side here, multiply everything by 4. Then you get minus 46,4, right? Minus 46,4. So you've got minus 46,4 meters. Now, what does that tell you? What does that, let me write my meters. This minus 46,4 has a negative attached to it. This 46,4 has a negative attached to it. What does that mean? You remember from the first video, it means that from the point at which this object was thrown to the point where it's just about to bounce off the balcony, the height the ball moved by 46,4 in the negative direction, right? In the negative direction. So I'm not saying it moved 46,4 that way. No, I'm saying from the point at which it was thrown to the point just before it bounces off the balcony, you've got minus 46,4. It's a displacement, and you measure a displacement in a straight line. That's very important to understand, right? Displacement is measured in a straight line. So from there to there, straight line to where it is currently, which is there, that is 46,4. Now, the 46,4 has a negative attached to it because it moved down from its starting point. Its starting point is there, right? That's why it has a negative attached to it. Okay, so that's what that means there. This is very important to understand. I'm going to draw it up here again just to make sure that you understand it. There's the building. There's your 60 meters, right? Your object was thrown from there. It went up and it went down there. It bounced off your balcony and then it moved down there. From that point at which it was thrown to there, displacement is measured in a straight line. That is 46,4, right, meters. Now, it is negative because it started off in a higher position and it ended up in a lower position. So it is negative because downwards is negative and displacement is a vector. That is what this 46 means, right? But this is not what we're looking for, right? This is not what we're looking for. What we're looking for is that delta H, which is your height of your balcony from the ground, right? It's the height of your balcony from your ground. But now we've got this delta y. We've just calculated this delta y, and we've established earlier on that 60 minus the delta y that you get here, 60 minus the delta y that you get is going to give you your h. 60 minus your delta is going to give you h. So now that we've got our delta y, you come here and you say, okay, so 60 minus your delta y is equal to your h. Remember now, the negative here was just to give you a direction, right? This negative was to give you a direction that, okay, from this point to that point, the ball moved downwards in the negative direction. It moved downwards in the negative direction, right? But this equation here is not an equation of motion. So here you've got to be careful with the sign that you use. This is not an equation of motion. Here you've got to be careful with your sign. You use logic, right? You use logic. So if you've got a building that is 60 meters tall, which is that 60 there. Building is 60 meters tall, right? And then you've got a balcony with a height above the ground. And then you've got a height there, which is 46,4. 46,4 meters. You will see that this minus that is equal to that. Okay, so this is logic. This is not an equation of motion. So here sign convention doesn't matter. Here logic matters. Okay, you can clearly see with your eyes that if I've got 6 and 6 is my total height, I'm sorry, not 6, 60. 60 is my total height, and this total height is made up of h and 46,4. Then you can see that if I take these two heights and I add them, then I'm going to get 60. Therefore, if I subtract one of these two heights from 60, then I'm going to get one of the two heights, right? So in this case, I've got 46,4. So I know that h, which is the height of the balcony above the ground, is equal to 60 meters minus 46,4 meters, right? And then if you take that, that's the height of the balcony above the ground. So this is, I'm just going to clear this, and then you say 60 minus 46,4. That's going to give you 13,6 meters. So the balcony is 13,6 meters above the ground, and this is your answer, right? Meaning that if you take 13,6 and you add it to 46,4, then you will get 60. You will get 60, which is the total height of the building. Okay, so just remember, with these questions, test yourself and always check your answers and see if your answers make sense. I think that's the biggest skill that I want to impart. Know how to check yourself and know how to check that your answers make sense, right? So if you say 13,6, which is what we just got now, plus 46,4, you get the 60 that you started off with, which is the total height of your building. So you know that your answer is correct and that the height of your balcony above the ground level is that number there. Okay, so this is an example of how to go about thinking about and solving and approaching a vertical projectile motion problem. I know I'm being very slow, but I'm intentionally being slow so that I hammer these points across, make sure that they hit home, and make sure that you understand. I might be too slow for a lot of students, but this is very intentional. Okay, so this is how you answer these questions. This is how you tackle vertical projectile motion. I might cover more examples on separate videos. I took a bit of time to answer this specific question because it's my first question that I'm answering in this session or in this section or topic. So I will probably move a little quicker with the other questions in separate videos. Okay, so I will stop here. Till next time. Number one, listen, number one. Listen, number one, listen.